So with this differential equation, y prime equals 2x cosine squared y. If we want to draw a direction field for that, first of all, I'm noticing that since y shows up inside a trigonometric function, it's probably going to be most practical to label the y-axis in terms of multiples of pi, assuming this is a radian measure. So let's mark these as maybe pi, 2 pi, negative pi, negative 2 pi. And beyond that, it's just going to repeat anyway, because cosine is a cyclic function. So I think we can get away with just this range. And then for x, maybe we try 1, 2, 3, 4. Just to establish a range that we're talking about here. And of course, these axes are not necessarily to scale with each other. But to draw out a direction field, one way we can start approaching this is by just picking some points on the graph and calculating for that x and y value, what would y prime be? Because ultimately a differential equation tells you at a certain xy coordinate, or whatever the variables happen to be, what's the slope at that point on the graph. For example, if we plug in, let's say 0 for x and 0 for y, the origin. You plug in 0 for x and 0 for y, what do you get for y prime?
Zero?
Yeah. That whole thing's going to be 0. So at this point, at x equals 0, y equals 0, the slope would be 0. We would just have flat. In fact, where else can we guarantee that the y prime value will be 0?
All of x? Like x is equal to 0?
Yeah, in general, regardless of what y is, y could be anything. If x is 0 in this equation, then the slope will be 0. So we can say that every place where x happens to be 0, in other words, the entire y-axis, the slope has to be 0. So we can fill all of those points in at once. We don't have to check individually each one. We can say everywhere on the y-axis, the slope will be 0. In other words, if the graph passes through this point, it has to be flat at that instant. We can also go a little further than that, though. Let's assume x is not 0. We want to know where else is y prime 0. So let's say 0 equals 2x times cosine squared y. We've already established that if x is 0, that makes the slope equal to 0. But what y values will guarantee that cosine of y becomes 0? Yeah, 2 pi should work, right? Cosine of 2 pi, wait, is that right? I think it's sine of 2 pi is 0, right? Cosine of what value would equal 0? Yeah, pi should work. Because the cosine graph, if you take a look at cosine on its own, it starts off at 1, dips down to 0 when we get to pi, and also at negative pi. So when y is pi or negative pi, all those locations should also have slope 0, regardless of what x is. So if y equals pi, then the slope is going to be 0 no matter what x is. And if y is negative pi, then the slope is 0 no matter what x is. And we can also extend this because the cosine is cyclic. If you go to 3 pi or 5 pi, any odd multiple of pi as the y value will have 0 slope. Let's try a few other points. Actually, before we move on, any questions on this so far, this direction field idea? Then let's test out maybe what happens when, well, we already know when x is 0, it's always going to be 0. Let's say x is 1. And y is, let's say y is 0. Then we get y prime equals 2 times 1 times cosine squared 0. What's that going to be? Yeah, it should be 2. 2 times 1 times 1, because cosine of 0 is just 1. So at the location 1, 0, the slope is going to be 2. And where else would we get the exact same result? What other y value would lead to cosine squared y being just 1? What angle causes the cosine to be exactly 1? Yeah, any, specifically any, we already got odd numbers times pi are going to be 0. But should be 2 pi should work, right? So if y is 2 pi, cosine of 2 pi would also be 0. Or sorry, would also be 1. Because again, the graph of cosine starts at 1, dips down to 0, then -1, then 0, then +1. So that's going to hit 1 at 0 and 2 pi. Wait a minute. What is it at pi? I think we missed that. At pi, what's the value of cosine? Yeah, cosine pi is -1. So let's rethink this a little bit. Cosine of pi is not 0. What angle would y have to be to make this 0? Yeah, cosine of pi over 2. So when y is plus or minus pi over 2, then cosine is 0. And also 3 pi over 2 should also work. Pi over 2, 3 pi over 2. So those values, those y values will lead to 0 slope. So pi over 2, 0 slope at any x value. 3 pi over 2, 0 slope at any x value. Negative pi over 2, 0 slope. Negative 3 pi over 2, 0 slope. But if we look in between, 0 or 2 pi lead to the result being 1. Also, we're not just taking cosine of y, we're squaring it. What would you expect to happen to this graph if you square the result? Specifically, what happens to a negative value when you square it? Yeah, that jumps up to positive. So the graph of cosine squared is going to look more like this. That region that would be negative becomes positive instead. It still only goes up to 1 because -1 squared is still +1. But it looks like we're going to hit cosine squared being 1 when the input is 0 or pi or 2 pi, or also negative pi and -2 pi. So all of those y values, 1 or pi, 2 pi, -2 pi. So yeah, it looks like it really is any integer times pi. So any integer times pi results in cosine squared y being 1. So in general, if y is a plus or minus any constant, any integer times pi, then y prime is just going to be 2 times x times 1. So for instance, when y is 0, we can just say when x is 1, we get slope 2. When x is 2, we get slope 4. When x is 3, we get slope 6. So it just gets steeper and steeper. Or when an x is 1/2, we get slope 1. We could even go to the negatives. When x is -1, we get slope 2 times -1, so -2. Then -4, and so on. And we could even fill in the in-betweens. So we can fill in a bunch of data points, individual locations, and how steep it would be at those individual locations. Same thing up here. When y is pi, cosine squared of pi will also be 1. So the slope is just going to be 2 times the x value times 1. So same thing, flat, slope 2, slope 4, slope 6, slope -2, slope -4, and so on. Any questions on that so far? And I guess this really does repeat cyclically. If we go to negative pi, we get the same thing. Cosine squared of negative pi is still just 1. So we get slope is 2 times the x coordinate. Something like that. So this repeats cyclically, looks like with a period of just pi, every pi it repeats itself. And we could, of course, fill in more details as well. If we fill in, let's say, if we get closer to this line, or let's say closer to y equals 0. When y is very close to 0, what would you expect, or not 0, let's say pi over 2. What happens to cosine squared y when y gets close to pi over 2? Going back to this graph, we know that when the input is pi over 2, exactly, then we're at 0. What if you're just kind of close to pi over 2? What would the output be? If you're at pi over 2, but just go a little to the left or a little to the right, yeah, it's going to be pretty close to 0. Like if the input is pi over 2 plus a little tiny bit, the output is pretty close to 0. And note that it's positive on both sides. What that tells us is when y is not pi over 2, but close to pi over 2, we're going to get a slope very close to 0, but just a little bit positive. So everywhere near this horizontal, the slope is going to be positive times x. So if x is positive, we get a very weak positive slope. If x is negative, we get a very weak negative slope. And that's true on both sides of the line, above and below. And then same thing with this horizontal. If we're exactly at this y value, the slope will be 0, because cosine squared of negative pi over 2 would be 0. But if we're just close to this y value, cosine squared y will be a little bit above 0. A little bit above 0 on either side. So we'll have tiny positive number times a positive x value will be a tiny positive slope. Tiny positive times a negative x value will be a weak negative slope. So I would expect the direction field to look a little like this. Every point where x is greater than 0, yeah, at all locations where x is greater than 0, the derivative is positive, or it could also be 0, but it's at least non-negative. And likewise, for all these locations where x is negative, the slope is negative or 0. Because cosine squared y is always non-negative. So there's no way this can be negative, which means x is what chooses whether the result is positive or negative. So it looks like we're getting a general idea of the direction field. I guess we could fill in some more slopes here and here. And this is pretty much just a rough sketch. This is not really to scale. But I think this at least gets us a good general idea of what the shape is starting to look like. Any questions on the shape of that direction field so far? And at this point, we can also, I think we now have enough information, we can sketch out some of these sample solutions. Because the direction field is basically just a visual representation of the differential equation itself. The differential equation says for any x, y value, you can calculate the slope. The direction field for any x, y value shows you the slope at that x, y value. It's the exact same information. The slope at each x, y value is just shown visually instead of algebraically. And also, much like a differential equation, if you just got a differential equation, how many solutions would you expect? Or let me pose you a more basic version of essentially the same question. If I tell you the slope of a line, like let's say I want a line with slope 3, how many lines are there with slope 3? A lot. Specifically, how many a lot? If I just say, draw a line with slope 3, yeah, there's infinitely many possible lines with slope 3. Because if I just tell you the slope, what am I not specifying? What other important property of a line is not specified if all I tell you is the slope? Usually to graph a line, you'd want to know the slope and also what else? Well, you can create the function if you know the slope and also what other piece of information do you usually need? Yeah, some point that it passes through. The intercept would be one example, but you could really do this with any single point that it passes through. If I just say, draw a line with slope 3, you could draw this one or this one or this one or this one or this one. There's infinitely many lines with slope 3. But if I also specify that passes through the point 0, 5, only one of them fulfills that condition as well. With differential equations, there's a very similar result. The differential equation tells you something about the slope of the curve. If all you know is the differential equation, you should usually expect infinitely many solutions. There are infinitely many functions that match this description of how the slope relates to the location. But if you also specify a location that it has to go through, like let's say this differential equation and the point, let's say 1 pi, a point that it has to go through, that should narrow it down to just one solution. And we can sketch that solution from the direction field by following the lines here. Like at this point, we know it has to have slope 2. But as we go up, we get to a region where the slope is flatter and flatter and flatter. And this horizontal here, the region at y equals 3 pi over 2, where the slope is 0, should be an asymptote. It's going to get closer and closer to flat, but never quite become flat. Or if we go in reverse, we get to a region down here with weaker and weaker slope. So it should become flatter and flatter. And remember, we decided earlier that at the y-axis, when x is 0, the slope has to become 0. It's got to flatten out. On the other side, it looks like it now has a negative slope. So following the curve to this slope lines here, we get something that looks kind of like this. So it looks like this curve should be a solution to the original differential equation. And note that we haven't even tried solving this analytically. All we've done is draw the shape of the directions specified by this equation, and then we can sketch in curves that match those directions. Alternatively, let's say we start here. This says flat, but then a little ways to the right, it's now a steep upward slope, and then less steep, flattening out. Or to the left, we've got flat, a negative slope, steep, and then less steep and less steep. So it looks like we get another similar looking curve. Solving it algebraically, this one is actually going to be very problematic to solve algebraically, largely because of the fact that we've got this cosine of y. Generally, it's a lot easier to solve a differential equation if it's just some function of x times y. If you've got something more complicated being done to y, that differential equation is nonlinear, and that's much more difficult to solve. This one actually is separable. We could potentially solve this by separating variables. So let's try solving that after we do a little bit more with the direction field. One other thing I want to emphasize, let's say you start at y equals 3 pi over 2. At that location, what's the slope? Yeah, if y is 3 pi over 2, cosine of 3 pi over 2 is 0, so we go flat. But if we go a little to the right, y is still 3 pi over 2, so now what's the slope? Should be still 0. If y is still 3 pi over 2, cosine squared of that is still 0, so we're still flat. And no matter how far to the right we go, y is still a value that makes the whole thing 0. So this line is actually, this curve is actually just going to be a flat line. This is one of the solutions. Same thing with, for instance, y equals pi over 2. This is also going to be a flat line solution. And so is negative pi over 2, negative 3 pi over 2. Some of the solutions to this are horizontal lines. Y equals a constant value. Other solutions follow much steeper trajectories. And you can sketch these just by picking a point and following the curve to match those direction arrows. But it looks like they're all going to follow this general pattern. Sort of a asymptote, then dip down, then curve back up, then asymptote. And of course, some of them are the actual horizontal lines that form those asymptotes for the other ones. But note that we were able to sketch out what these curves can be expected to look like without even solving this, just by drawing the direction field. Any questions on that so far? And it's also possible to do this using computer software as well. There's a great computer program, a variety of computer programs really. One that I'd like to show off right now is called DField. Pull this up. DField is this really nice program that allows you to rapidly graph direction fields. So for instance, if we just type in y prime equals, what was it, 2x times cosine y squared. And let's have that go from, just like we had here, from -2 to 3, and y going from, let's say, -7 to 7. Graph phase plane. And so here we see what that direction field looks like. And we can click on various locations to put in sample curves. And note that this is pretty much exactly what we were seeing on the marker board as well. We get this cyclic pattern of asymptote, dip down to a curve, dip back up, asymptote, and some of the solutions being horizontal lines. The advantage to the computer program version, of course, is that it's much faster. You can very rapidly just get the direction field instantly and graph a whole bunch of these sample solution curves. I would definitely recommend trying out at least a few direction fields by hand to get a feel for how exactly it works. But once you've got the general idea, computer software like this can be really useful for that. Any other questions on the direction field so far? All right, let's see if we can solve this analytically, or at least get a start on it. The fact that y is wrapped up inside this cosine function makes this differential equation nonlinear, which is usually really awkward and difficult to solve. But the fact that it's a function of x times a function of y separately, function of just x times function of just y, means this equation is separable. We can split it up into x's on one side, y's on the other side, and hopefully be able to integrate. Best approach to direction fields with trig functions. The trig functions often make the direction fields a lot trickier. I would usually try, start by writing it out point by point, like just try a few sample points and see what you get. But look for patterns in the cyclic patterns or cyclic behavior of the trigonometric function. Like look for, like we were looking at earlier, ask yourself what inputs always cause this to become 0 or always cause this to become 1 or -1. Look for the easy values to start with as sort of building up a frame of the direction field. Sometimes that alone is enough information. But even if it's not enough information on its own, it at least gives you a framework to start looking for, okay, what's happening between those easy values. And then once you've got a general idea by hand, also take a look at computer software to draw it like DField there and compare the results. But let's see if we can solve this analytically. First of all, let's write out y prime as dy over dx. what we want to do here, the idea of separating variables. We want to split this up so we have just x's on one side and just y's on the other. And the reason for that, we've got a derivative here. What's the opposite of a derivative? An integral. We'd like to be able to just integrate both sides with respect to x, so these cancel out. But we can't do that just yet. On this side, they would just cancel out, so we just get y. On this side, though, we can't integrate this whole thing with respect to x because y itself is a function of x that we don't know yet. So we can't just integrate with respect to x yet. But what we can do is get rid of this y part. Because this cosine squared y is a function of y being multiplied by a function of x, how can we just get rid of cosine squared y entirely? What's the opposite of times cosine squared y? Yeah, we can just divide. If we proceed by dividing both sides by cosine squared y, then on the right side, we're left with just 2x. We still have a mixture of y's and x's over here, but how could we get rid of this dx here? Yeah, so we multiply both sides by dx. And formally, we're not really multiplying by dx because dx isn't a number. But this is essentially a shortcut for a longer method using the chain rule that still works out to the same thing. Yeah, that's a good thing also, to look for, try plugging in values that lead to pi, 2 pi, easy multiples of pi, and see what leads to 0 or 1 or -1. And yeah, that is going to be a repeating pattern. So you really usually just have to graph out one cycle of that pattern, and then you know the rest is just going to repeat. So let's see what we get here. We multiply both sides by dx, which again is really just a shortcut for a longer method involving the chain rule that leads to the same thing anyway. Divide both sides by cosine squared y, and we get 1 over cosine squared y dy equals 2x dx. At this point, we can say we have separated the variables. One side of the equation only has y's and dy's. The other side of the equation only has x's and dx's. So at this point, what can we now do? Yeah, we can integrate both sides. And we don't really even need to specify what we're integrating with respect to. It's already built in with the dy and the dx. Integrate this function with respect to y, integrate this function with respect to x, as already specified. And 1 over cosine squared y looks kind of inconvenient at first, except what is 1 over cosine? What else do we call that? One over cosine theta is defined as, yeah, that is just the secant theta. So we can write this 1 over cosine squared. It's not actually going to be a logarithm in this case, because if it was just like 1 over y, that would become logarithm of y. But 1 over a more complicated function of y, that's not guaranteed. You'd have to use some sort of u substitution instead. But we don't even need that in this case, because 1 over cosine squared can just be written as secant squared. And do you happen to remember a function whose derivative is secant squared? If you think way back to early calculus. Derivative of what function is secant squared? Does that look familiar? Yeah, the derivative of tangent of y is secant squared y. So if derivative of tangent is secant squared, then integral of secant squared will be just tangent. So this whole thing just becomes tangent of y. I was really worried about that cosine squared in the integral, but it turns out it's just secant squared, so that turns into tangent. Very convenient. And yeah, good idea to review that table of integrals and basic derivatives, because those are going to be showing up a lot in differential equations. And then integral of 2x is going to be what? Yeah, it should be x squared, because we're taking the integral. So you add 1 to the exponent, x squared, and then divide by the new exponent, which cancels out the 2. Or to put it another way, you could think of it as what's a function whose derivative is 2x? X squared is a function whose derivative is 2x. Also, since we're looking for all possible solutions, what else should we include here? Yeah, we should include plus a constant. And you really only need that on one side. If you included a plus another constant on the other side, you could just subtract that from both sides and then combine the two unknown constants into another unknown constant. So tangent of y equals x squared plus c. And then that is a solution. We would say this is the implicit form of the solution, in the sense that we've canceled out all the derivatives and integrals. But ideally, what else should we do here? If we really want to say this is the solution, what would be a good last step to take? Isolate. I probably wouldn't isolate x here. Instead, isolate, what are we really trying to solve for? Yeah, ideally, we're trying to find a function, find y as a function of x that makes this differential equation true. Ideally, we want to get y equals some function of x. So what's the last thing we need to do here to isolate y and get an explicit solution? How would we get rid of this tangent function here? Yeah, an arctan or inverse tangent function. So we could say y equals inverse tangent or arctangent of x squared plus c. That would be the same solution, but written in explicit form instead. Explicit means we've actually isolated y. We've got y equals some function of x, as opposed to implicit form, which is the solution, but it's written as just some relationship between x and y rather than y equals something about x. So this is the explicit form of what we would call the general solution. General solution in the sense that it's infinitely many solutions, because c could be anything. How do we know what c is? If we just want the general solution, we would leave c as an unknown parameter. We want to say, we're essentially listing out not just one function, but the entire family of functions that would make this true. And in fact, if you graph these, if you like plug in various c values and graph this, you'll end up getting the various curves we were looking at on the direction field. So those curves we drew are just graphs of this function using various different values for c. If you wanted to solve for c, though, what other information would you need? Again, going back to the idea of a line, if I just tell you the slope of a line, there's infinitely many solutions. What other information do you need to narrow it down to one solution? Yeah, you need x and y values. You need a point on the graph. So let's say we also know a point on the graph. Maybe we know that this passes through the point maybe 0 pi over 4 or something like that. You could plug in 0 for x and pi over 4 for y. In fact, going back to this implicit solution might be more useful here. Plug in 0 for x, pi over 4 for y, and then c is the only unknown, so you can solve for c. Fill that in your general solution, and you now have the specific solution going through that point. So that's usually called an initial value problem. Initial value problem, or IVP, means a differential equation along with an initial value, some point that the graph goes through. The differential equation gives you a family of solutions, infinitely many solutions, typically tied together by some unknown parameter, usually c. But the initial value, plugging that in for x and y, allows you to solve for c to find the specific solution. So for instance, in this case, you take tangent of pi over 4 equals 0 plus c. So c would just be tangent of pi over 4, whatever that is. Fill that in for c here. And there is the specific solution with the value of c included. Any questions on that? Or any other general questions or anything else you'd like to work on? Match a field with some trig function differential equations. Like here's the direction field, try to find which differential equation it matches. Yeah, do you have an example of that we could try out? If you could share a screen or send me a screenshot or something, we could take a look at that. I think just as general advice, I think what I would do is I would start by looking for any location or locations where the slope is 0, because those are usually the easiest ones to identify. Like with this one, we were looking at it in terms of like what x values would lead to the whole thing being 0, what y values would lead to the whole thing being 0. Figure out what locations you would expect to have 0 slope for each differential equation, and then take a look at the direction fields that are provided and see if any of those have 0 slope at those locations. And then also, if you've got multiple matches, maybe take a look at the regions in between the regions that are 0. Is it positive slope or negative slope? And then compare that to the differential equation. Would those x, y values lead to positive slope or negative slope as expected? So compare it point by point. And again, starting with the locations where slope is 0, because those are probably going to be the easiest to analyze. Any other questions on that idea? Or any other examples you'd like to try out? And let me paste a link here into this D field thing so you can try this out for yourself. You can find it. Yeah, there it is. If you go to, I'll paste this into the chat, this website, cs.unm.edu/tildejoel/dfield has a couple of JavaScript applications that allow you to graph a direction field really quickly. And you can probably find other web-based ones as well. This is just the one I usually use. You can just type in the differential equation. It'll show you the direction field, and then you can click at various locations to set initial value points, and it'll automatically graph the curves. Yeah, you can very much think of that as a proof by contradiction thing. Say this one should have slope 0 at certain locations. Does that actually match the differential equation or not? So yeah, look for breaking points. Like this one has to have 0 slope at these locations. Does that actually match this graph or not? Any other questions on direction fields? All right, then I am going to go get ready for a meeting, but feel free to let me know by email or on Discord if you have any other questions, and I will see you next time.